Before I get started, are there any questions? So we're still in review mode, and I do want you to start to think about your project and your data and your research question, because time is going fast. So today I'm going to review some more, and depending on how fast it goes, I may have to leave a little early because I need to catch a plane. So I won't be in for office hours today, but then Monday I'll be around, and next week, Wednesday, I'll be around. And if you need to see me outside of the office hours, I'll be here on Tuesday as well. So send me an email and we can schedule something. But I really, ideally, would like to speak with every one of you before you submit your research question or speak or email, so that I know you're on the right track. Because, and you know, I've said this before and I'll say it again, you often get trapped where you think you have a really good question and you think you have really good data, but your data is not quite ready for prime time, and then you end up spending 6-7 months getting your data ready and you have no time to do the analysis. So that's what I don't want you to do. So there are no questions. Let me start. As I said, this is a review for many of you. I mean, I'm assuming you know this stuff, but it might be a good refresher, and at least it gets us all on the same page in terms of terminology and notation and all those kinds of things. And maybe some notions about asymptotics that you might not have been exposed to, depending on what kind of a regression or econometrics class you took. Some people stress this, some people don't. So I'm going to start by just very quickly going over ordinary least squares, basically stressing the statistical framework in which this works. So assumptions, things that are called regularity conditions, basically all the rules you have to follow for it to work. And then we'll cover very quickly some non-spatial diagnostics, specification tests. So in a couple of weeks we'll switch to the spatial ones, but before you do the spatial ones, we'll cover the non-spatial ones. By no means comprehensive treatment. Basically, I'm giving you background on what GeoDa gives you and what GeoDa space gives you as the non-spatial diagnostics. And then we switch to instrumental variables and two-stage least squares, a little bit of notion of asymptotics and how this machinery works. Maybe not so much for you to know it that well, but for you to be able to read the literature, and when you see things in papers that you know why these weird things are being done. I've always thought they were weird, but till I figured out what it was about, and then they're not weird at all. So that's where I want you to be. And then if we have time, I'll run through this in GeoDa space, just a quick demo, but it's documented extensively in the book. So these are the chapters that deal with ordinary least squares and two-stage least squares and all the non-spatial stuff. Spatial stuff we'll deal with later. Okay, so we start with ordinary least squares estimation and just some basic notation, and also stressing a point that is often forgotten, is that a linear regression is just that. It's linear. So it's an approximation. Really what regression is about is modeling what we call the conditional expectation. So the mean of the dependent variable conditional on knowing something in terms of the x variables, the explanatory variables. And we are assuming, because it is an assumption, that that relationship is linear. And sometimes that's a good assumption, sometimes it's not so good. So basically, we relate the observation on a dependent variable, y, at location I, to a sum of explanatory variables, each weighted by a coefficient, the regression coefficient, and an error term. The error term is a random error term. This is not the residual. This is a mathematical construct that we use to get the statistical properties of estimation. So beta in classical statistics is an unknown constant. It's not a random coefficient. In Bayesian statistics, it is a random variable. In classical statistics, it's a constant. And obviously, we don't know this constant. This is a population constant. The purpose is to use the data, the sample, to get an idea, an estimate for that unknown constant. And the randomness in this setup all comes from the error term. So whatever we assume about the randomness of the error term will affect the randomness of the dependent variable, and only the error term. And then, of course, to keep our life simple, we could also do it differently, but to keep our life simple, we assume away any systematic error. In other words, the mean, the average of the error term is 0. So on average, there is no error. Basically, that's what it means. Otherwise, you would systematically overestimate or underestimate right off the bat, and that doesn't make any sense. Okay, in matrix notation, same thing, but now we have vectors and matrices. So now our left-hand side is a vector of dimension n, where n is the number of observations by 1, so column vector, equal to a matrix product, a product of a matrix times a vector of coefficients. So the matrix is n by k, and the vector is k by 1. So the result is n by 1, right? So they're compatible. And this product, later on, after we have an estimate for this unknown beta in hand, that will be our predicted value. The predicted value will be the product of the observed explanatory variables, the x's, times the estimates for the coefficient. And again, that is a vector that we can then match to the observed vector of the dependent variable. And E, or epsilon in some notation, or U in some notation, is the error term, is a vector, n by 1 vector of mean 0. Now this is a vector mean, okay? So these are simple extensions, and basically we do this to keep the notation simple. Otherwise, you'd have to keep using all these subscripts and these summations, and that just gets really messy very quickly. So we go to the matrix notation. And as I mentioned, or quote unquote warned you earlier, I will use matrix notation throughout. That's basically the only way to deal with spatial models. So it's all about the conditional expectation. And this conditional expectation is linear in X. That's why it's a linear regression model. So basically what we're saying is that the expected value, so that is not the value exactly, that is the value on average, right? Because we have randomness. We have randomness in the error term. So we're never, even though it looks like we're exactly on target, we're actually not. We're dealing with something that has random variability in it. That's why we're interested in the precision of the prediction, in the precision of the estimates, to quantify the variability, to quantify the uncertainty. So basically, when we have a linear regression model, we can write out the two parts as expected value. So the expected value of x beta given x. X is not random. Beta is a constant in the population. So the expected value of a constant is a constant. That's x beta. The other part is not a constant. And this is where we start making assumptions. And we assume, and we'll get to that in a second, we assume that this error term is not correlated with the explanatory variables. That's an assumption of exogeneity that you may be familiar with. If that's not the case, as we'll see in a few minutes, then all bets are off. But if this is the case, then the second term, on average, disappears. On average, there is no error. And if the error is not correlated with x, then for all practical purposes, x is a constant, so we don't have to worry about it. So on average, that washes out. So on average, the value of the dependent variable, conditional upon, meaning given that we know values for x, is a linear function in x. Very simple. Okay? Now, this is an assumption. In a lot of situations, this conditional expectation still exists as a concept. What is the mean of the dependent variable on average given these x variables, but it may not be linear. Okay. And so this is a, if you wish, a linear approximation to a very general concept. Okay. And if the linear assumption holds, we're good. If it doesn't, we may be in big trouble. Okay. So important also to remember what are we really interested in. In a lot of contexts, we have two interests, right? Nowadays, a lot of interest in prediction, predictive analytics, right? Prediction is one thing. But in a lot of prediction, you don't really have to know much about the coefficients. You just want them to work well in an out-of-sample situation. But if you're interested in inference, in understanding underlying mechanisms or processes, then you're interested in how much does my dependent variable change if I change some of the right-hand sides. So if I increase people's subsidies to go to the doctor, how much more will they go to the doctor? So we change x, we look at the effect on y on average, right? So in a linear regression, I mean, technically this is the partial derivative, but since it's linear, that's just a constant. In a linear regression, the marginal effect, the effect of a change in one of the explanatory variables on the dependent variable is constant. In other words, if you change the subsidy, it doesn't matter whether you're a poor person or a rich person, your change in using the doctor is the same. It's beta times the change in the subsidy. Okay? Is that a good assumption? Maybe not, right? And that's where nonlinear models come in. In nonlinear models, that marginal effect actually depends on the value of x. So for a high-income person and a low-income person, it would be a different effect. But in a linear model, you can't have that. In a linear model, it's the same for everybody. So that's a major simplification, if you wish, of complex reality, which may or may not be a decent approximation to what actually goes on. But I keep hammering on this because all too often we stick with these linear regressions and then we're surprised that we have bad results. Well, one reason you might have bad results is that the phenomenon you're modeling is actually highly nonlinear and you're forcing it into a linear framework, and that may not be that great. Okay, now a little technical, just some jargon, some vocabulary that you may not be familiar with. First of all, and then my particular take on it to put it a little bit into perspective. So the first assumption is that x, your exogenous variables, are non-random, non-stochastic, or as you may have seen in textbooks, fixed in repeated experiments. That is pretty meaningless. Basically, it means that the randomness, whatever randomness may be in x, of course there's randomness in x, but it doesn't matter. It's inconsequential. So in the old days, that was expressed as fixed and repeated experiments. If you, in fact, put yourself in an experimental situation, right? You have a treatment, and then you have a control. So you just keep that the same over and over again, then you can get certain statistical properties. In our setting, it will be a little bit more abstract. Basically, what we're concerned with is that whatever randomness is in x or may be in x doesn't matter for practical purposes, right? And so typically that is done by putting some bounds on the kind of variables that you might have. This makes sense, for example, if you model the stock market, where the bounds on the second moment translated, that means on the variance, on the spread around the mean. So if you don't have an extreme spread around the mean, what does that mean? It means you can't get crazy values. In the stock market, you can get straight crazy values. So this type of constraint in those contexts may not be that realistic. So keep that in mind when you apply your model to particular circumstances. Is it reasonable that your explanatory variables are within a given range and can't go crazy, right? And in a lot of socioeconomic applications, that is in fact the case. You know, if you have, you know, incomes or unemployment rates, I mean, these are all fairly reasonable. The error term, the randomness part, and this is where a lot of the spatial stuff will come in. The standard assumption is that these errors are independent, uncorrelated. So the precision in one observation is unaffected by the precision in another observation. And also this precision is the same everywhere. So the variance is constant. This is called homoskedasticity. The reverse is heteroskedasticity. So heteroskedasticity means that the precision varies by observation. So for lower income people, you have better precision than for higher income people, for example, which is a common situation in surveys, right? So that can be in the classic model. In the classic model, it's all the same. And then finally, an important one is that these exogenous variables, the x variables, are uncorrelated with the error term. So what I call the signal is the x, and the noise are not correlated. So in other words, if you have explanatory variables, it's the same kind of thing, right, with the heteroskedasticity. But it's a correlation matter. It's not just the variance. It's the actual correlationship of the two variables. If you have, say, higher or lower income and the error term is correlated with that, you can't have that. And how, I mean, mathematically, it's easy to express that, but more intuitively, what does this mean? This means that some of the phenomena that you take as explanatory factors are in fact explained by the same system as your dependent variable. So, for example, the illustration I use in the book is you have a crime rate and you use unemployment rate as an explanatory variable for crime rate. But there is a literature that also has the reverse and says the crime rate is actually an explanatory variable for the unemployment rate. You know, if you have too high crime rate, nobody wants to do business in that area, so there are no jobs, right? Or, you know, if you're unemployed, you have nothing else to do, you're going to commit crime. So there's the two sides of the same coin. So you really cannot maintain that in one context, one of these is determined outside the system, but then in another context, it's not. So when you have that kind of situation, it's typically untenable to maintain that the explanatory variable is uncorrelated with the error term, and you have to then take that into account, in the sense that there are two sources of variability. In the classic model, there's only one source of variability, that's the error term, the random error term. But if there's also variability in your endogenous variables, then you have to correct for that. So then, you probably all know the Gauss-Markov theorem that spells out under a set of assumptions, and I keep stressing that because if these assumptions don't hold, then the rest may not hold either. Some of it does sometimes, but not everything does all the time. So under this set of assumptions, then we can actually prove that the least squares estimator, which is basically a solution to a system of moment equations, and I say that now because we'll revisit that in 4 or 5 weeks when we deal with generalized method of moments. So it's a solution that is expressed in that equation that you probably all have imprinted in your brain, x prime x inverse x prime y, right? And one can show that, first of all, this estimator is unbiased, and that's very easy to show. So you just spell it out and replace y by its population expression, x beta plus e. We have the first matrix product, which gives us x prime x inverse times x prime x, which cancels out, so we just have beta, the population value. And then on the second part, as long as we're assuming that x and the error term are uncorrelated, then the second part, x prime e, becomes 0. X prime x inverse is a constant. We don't have to worry about it. So then that shows that the ordinary least squares estimator is unbiased in the sense that on average it gives you the population parameter. And you may say, well, what does this mean on average? Because I only do this once, right? And so in the old textbooks, it would say if you would repeat as many times, then on average you would get the population parameter. Here you can think of it more as a mathematical framework that says that the estimator is unbiased, which means that there is no systematic under or over prediction. Right? And then you can also show that of all the unbiased estimators, this is the one that has the smallest variance. In other words, is the one that has the greatest precision. So how do you carry out inference? And let me step back a second. You know, what is inference really about, right? And inference is about a situation where you want to say something about a population without observing the population. And I want to step back for a second because this day and age in a big data world, more and more we get into situations where we actually have the population. And in those situations, inference in this classical sense doesn't necessarily make a lot of sense. It doesn't make a lot of sense in a practical way because all your standard errors will be so small, computed in this way, they will be so small that for all practical purposes, everything will be significant. And why will they be small? Because you divide by n. If n goes to infinity, the variance estimate goes to 0. Okay, everything else being the same. So that's a practical thing, but conceptually also, you know, if you have the population, what do you need inference for? Inference is about saying something about the population parameter, right? So you have a sample, you estimate a regression relationship in the sample, and from that you try to say something about the population which you do not observe, right? But if you observe the population, you don't need to do that. Whatever you estimate is it. That's the population parameter. That's the linear relationship that holds in the population. So think about that, you know, when you do very large data analysis. First of all, it's going to bite you because all these standard errors will be very, very small. But also conceptually, think about what it is that you're doing when you're trying to carry out inference. And that's why a lot of, you know, machine learning, data mining in very large data sets doesn't worry about inference. It worries about predictive performance, not about is this parameter that we estimate different from the population parameter, because for all practical purposes, it is the population parameter. So it's a different mindset. Okay, predicted value, as I mentioned already, is simply, you know, the weighted sum of the observed values times the coefficient, and you can do this in sample, and that's typically to get a measure of fit, but you can also do this out of sample, right? And then the residual is the difference between observed and predicted, you know. So, and as you know, if you include a constant term in a regression, then the residuals on average are 0. If you don't do that, that's not necessarily the case. So if you, I mean, there's usually in practice not a very good reason not to include a constant term, but every once in a while, for theoretical reasons, you might not do that. But then keep in mind that your residuals are not necessarily averaged to 0. So then you have to correct for that and actually compute the average of the residuals and take that out if you want to do something like an R-square or something like that. And then very importantly, the residual is not the error term. And we'll see that later when we talk about specification tests. In specification tests, we have to go through this kind of intellectual exercise where we have the residual, but we really want to say something about the error term, because the error term is the part that affects the properties of our model. So the error term is supposed to be uncorrelated. Here are these residuals. Can we say something about the correlatedness of the error term from what we measure on the correlatedness of the residuals, right? And with OLS, we can. In some other instances, it's not that straightforward. Then one final thing about OLS, or it's actually, yeah, OLS. So very often you, and in some textbooks, still primarily older textbooks, you have this problem: what happens if the error term is not well behaved? And so in this standard notation, that's sigma squared I, what happens when the error variance covariance matrix is a generic matrix? Call it omega. Some literature calls it sigma. It doesn't really matter. So you could have heteroscedasticity, you could have autocorrelation, spatial autocorrelation, serial autocorrelation. Okay. So the typical reaction is to go to generalized least squares, or more precisely, feasible generalized least squares, right? But there is also a tendency not to do that, because the problem with this kind of error variance covariance matrix is not bias. Ordinary least squares remains unbiased, but the measure of precision is not right. So if you use the classic, S squared, the sum of squared residuals divided by the degrees of freedom, that is not a good estimate for the true underlying variance. But that's the only problem. You still have an unbiased estimator. If you go to feasible generalized least squares, you lose that unbiasedness. Then we're working in an asymptotic world. So asymptotic properties are properties that hold in an, imaginary, infinitely large sample size, right? And then you talk about consistency. But consistency is not the same as unbiasedness. Unbiasedness is a finite sample property. It always holds. Consistency always holds in the limit, but not necessarily in your given data set. Now, this is not going to be an issue if you work with very large data sets, but historically it was an issue if you work with 30, 40, 50 observations. Then you have to worry about that. So there is a literature, and we'll actually see a spatial variant of this, that says rather than going to this consistency business with feasible generalized least squares, let's just stick with OLS and fix the problem. And the problem is that our measure of precision is not right. And so we make this measure of precision more general, and then we see that, in fact, you can show this if you do the algebra, the variance for a general variance covariance matrix omega takes on this little more complicated form. And if you're good with linear algebra, you see if omega is sigma squared I, then all these x prime x and x prime x inverses cancel out, and we're back to our standard formulation of s squared times x prime x I inverse, right? So the trick is, how can we deal with this? And there's a classic paper by Hal White, and there's a similar paper in the statistical literature by Huber, which develop what is called a sandwich estimator. So that's a generalized estimate for the variance that takes into account the fact that this error variance covariance matrix may not be spherical, may not be sigma squared I. And the trick is, and it's a really interesting paper, it's from 1980, I believe. The trick is that rather than trying to estimate omega, which has n elements, and that's the same problem we saw the other day with the weights, it's an incidental parameter problem. You can't win this one. If you have to estimate n variances as the sample grows, you have more n's to deal with. So you can't win this one, right? However, what you can, and that's the beauty of that paper, what you can do is estimate the k by k matrix. Because if you look at the dimensions, this is k by n, n by n, n by k. So the result is k by k. And k is typically very small relative to n. So this is where the asymptotics kick in. Because k doesn't grow with the sample size, n does. K is the number of variables. So as long as the number of variables is small enough relative to the sample size, then you're in business. And then you can actually show how you can estimate or develop a consistent estimator for this middle term, and then you just plug that in, and you're in business. You have an appropriate measure of the uncertainty of the OLS estimator. And the same principle applies to two-stage least squares as well. So that's what we call the white estimate of standard errors or variance, and of course, GeoDa space has this. So given this regression, what can we do to make sure that all these various assumptions and regularity conditions are actually satisfied? And first thing we can do is some visual stuff. It's often helpful, but it's also notoriously unreliable. Because as I mentioned the other day, where our brains are wired to see patterns even when there are no patterns. So predicted value map gives you a sense of the smoothing of the results. So if you take the original variable, say crime, there's a data set in the sample data sets that looks at crime in counties in the US, and you map the crime, you may see patterns, right, and clustering and all that stuff. But the question is, to what extent can these patterns be explained by the patterns in the explanatory variables? So basically, after you control for the explanatory variables, you should see something very different, right? And so that's what your predicted value map can give you. It's a smoothing of the reality, basically. And then you see whether the high points that your model give you also match the high points that you observe. And an even better way to do that is, of course, with a residual map. And the residual map gives you the difference between the observed and the predicted. So high values, positive values, means that the observed is larger than the predicted, so the model under-predicts. So when there's higher crime, the model doesn't give you enough, right? And the low values is the other way around. The model says there should be more crime here than there is, given the explanatory variables. When you have extremes in this, outliers, then that means the model is no good for those observations. Large, extreme residuals. And if you have spatial patterns, that means that there may be something there that you're missing in your model. And we have to be very careful here for the reasons that I mentioned. So this is where we complement this, or we supplement this, I should say, with a formal specification testing, a formal analysis of the autocorrelation in the residuals. But a visual inspection would be something like this for the same variable. So this is what we call, and what GeoDa has as a standard deviational map. So the units of measurement are standard deviational units. So it's centered on the mean, 1 standard deviation, 2 standard deviation, 3 standard deviations away from the mean. So basically, when you see this dark blue and dark red, you are more than 2 standard deviations away from the mean in terms of your residual, which means these are locations where your model does very poorly, okay? Sometimes this can help you in identifying variables that you don't have in your model and you should bring into the model. And this can be a very useful exploratory aid when you look at these maps and you say, oh, why is it that all these reds are in this particular region? What am I missing there, right? What am I missing? Maybe I'm sticking an Appalachian dummy and all of a sudden my model gets much better. Something like that, right? So large residuals identify locations where your model does very poorly. Patterns in the residuals can also do that. And patterns in the residuals are a no-no. I mean, I should be more precise. Patterns in the error term are a no-no. The error term is supposed to be random. Random means no patterns. Okay? As I mentioned the other day, random is not interesting. You can't make any rhyme or reason out of randomness, right? So if you see structure, if you see patterns, if you see larger residuals, say, in urban areas than in rural areas, or you see larger residuals in the South than in the Midwest, then something is going on there that is systematic and really should be part of your model. So that's how you use these kind of maps and devices in an exploratory exercise where you go back and forth between the data, the model, the residuals, the data, the model, and back and forth. Okay? This is, of course, one particular way of approaching modeling. In a number of disciplines, this is a no-no, right? You develop your theoretical model first, and then you validate or invalidate that model by means of data. So it's very much a one-way street. You still need to do the specification tests, but maybe not so much to revisit the whole premise of the model and then restructure it and go around and around if you have a strong theoretical foundation that basically dictates what the model should be. But in a more of a data-driven analysis, which is more of the spirit of, you know, data science, I won't say data mining, but at least more data-driven analysis, there is this feedback between the model specification, the model performance, which you can visualize this way, and then revising the specification. So then there's also a bunch of non-spatial diagnostics plots. The one that I like a lot is a plot of the residuals against the predicted values, and that is a visual diagnostic for heteroscedasticity. Basically, what you would like to see is that these residuals, even though we're plotting residuals, but we're really thinking about the variance of the residuals. So the spread about the residuals around the mean is 0, we know that. So is this spread somehow related to the predictive performance of the model? And it shouldn't be. Remember, homoscedasticity, same variance throughout. So if we plot these residuals against the predicted values, we should see something that is kind of in a band, right? Not exactly a band, they're not all the same. Some are smaller than others, but roughly a parallel structure to the 0 line. And if we see something else, like this, and this funnel thing is very typical, and I was very happy that this particular example actually turned out this way, because it doesn't always turn out this way. But this funnel is a, you know, dead-on sign that you have heteroscedasticity. This shouldn't be the case. It should be kind of flat and within the same band, similar band around the 0 line, right? Now, of course, visual inspection of plots and maps can be very misleading. We can use it to suggest additional variables, but at the end of the day, there is really no substitute for a formal analysis, right? And we'll deal with that next very quickly. This is a standard output of what GeoDa gives you and also GeoDa space. So what I just wanted to do is very quickly give you a little bit of background of what these things are. So as implemented right now, GeoDa has a quick check on multicollinearity. Multicollinearity is about the extent to which your explanatory variables add an independent dimension to the analysis. You know, one problem in doing empirical analysis in the social sciences is that you often end up using census data. And a lot of the census data are different measures of essentially the same thing. You know, I call it badness, or you can call it goodness, but often it's badness. So, you know, crime, income, unemployment rate, all these things all point in the same direction. So if you do a regression and you have, say, 10 of these variables on the right-hand side, you don't really have 10 separate independent dimensions of explanation, right? And that's what multicollinearity is supposed to pick up. The condition number that we report is just one of many indicators that you can use. It's maybe a little old, a little dated. A lot of software also reports the variance inflation factor. Actually, that is included in PySal, but it's not in GeoDa space. Then a test on normality of the errors used to be a big deal, say in the 70s and the 80s. Not so big a deal now, because now we get the normality from the large sample. And so the asymptotics, which is the mathematical framework that gives us the properties of estimators and test statistics in, you know, hypothetical infinitely large data sets, that's what gives us the normality. That's why you hear the term asymptotic normality, which is actually a misnomer, as I'll point out in a few minutes. But so we have a test for normality, and then we have a bunch of diagnostics for heteroscedasticity, and I'll go over them in a second. First thing you notice, though, or maybe you didn't, is that all of these strongly reject the null hypothesis. So the null hypothesis is normality, forget it. The null hypothesis is homoscedasticity, forget it, okay? So basically, a lot of our sandcastle, if you wish, is already on very shaky ground, right? And the question then is, how much can we still say given that this is the case? Well, one thing we could do is make sure that whatever conclusions we draw are not really dependent in a strict sense on the assumption of normality. And this is what I mentioned, the asymptotics in many instances get us around that, so we don't have to worry about it. The other one is to draw conclusions that are robust to heteroscedasticity. And one way to do this, which I'm sure many of you are familiar with, is to use White or Huber sandwich standard errors, right? That gives you standard errors that are robust to the presence of heteroscedasticity. So there are a number of ways in which you can proceed this way, and we'll see later how that pertains to the spatial domain as well. So this condition number, it's classic textbook case. It's the ratio of two eigenvalues of the x prime x matrix after it's been standardized. X prime x is of dimension k by k, so that is no big deal, right? K is the number of variables in your model. And the classic rule of thumb is larger than 30. You have to worry about it. Shouldn't be taken too literally. If you want to see really high multicollinearity numbers, run a trend surface model. You get them in the thousands and even in the 10,000s. Basically what that means is that all these explanatory variables are highly intercorrelated. And then in the old days, you would have issues with numerical instability, but current software and hardware is much better at that and can even do inverses of near singular matrices and all these things. So it's not nearly a big issue as it used to be. As I mentioned, normality is in the textbooks and classic treatments is a fundamental assumption to carry out inference. Remember when I gave my regularity conditions, I didn't say anything about a normal distribution. And you do not need a normal distribution to obtain the optimal properties through the Gauss-Markov theorem of the ordinary least squares estimator. That says ordinary least squares is unbiased. You don't need normality for that. And has the smallest variance. You don't need normality for that. Where you do need normality is when you turn this variance into what we all know as a t-test, which is where we're bringing the normal distribution to carry out inference for the estimate of the coefficient. So everything about the optimality of least squares holds even for a non-normal distribution. But it's when you carry out inference that you bring in the normal distribution. So In the old days, that was a big deal because people had small data sets, and asymptotics, large sample theory, was a theoretical concept. You know, if you have 50 observations, asymptotics may be nice, but you only have 50 observations, right? If you have 100,000 observations, you can say, well, my asymptotics are fine. I mean, these large sample properties are probably kicking in for 100,000 observations, so you don't have to worry about it too much. So normality is one of those. As we will see later, there are things called central limit theorems, which establish the distribution of estimators and test statistics for a, you know, imaginary, infinitely large sample size, and these often give you asymptotic normality without having to assume it to begin with. You have to assume something. You typically have to assume, you know, bounds on the variance, and in the theoretical literature, these are often of the fourth moment. So you're working with, you know, not the variance, on the fourth moment of the random variable. So you're working with the tails, and you avoid thick tails, and thick tails are really extreme events. So basically you're saying, as long as there are no really crazy extreme events, this stuff will hold, will kick in. And this particular test, the Barrage-Jarque test, is based on the third moment, which is about skewness or asymmetry, and the fourth moment, which is about thick tails. And it's a chi-square with 2 degrees of freedom. You can also decompose it and do it separately as a test on skewness and a test on the thick tails. Random coefficient test, which is the Broich-Pagan and the Kunker-Bassett tests. They're basically a random coefficient model is one that allows the population coefficient not to be a constant, but actually a random variable. And this is where we get into the gray area between classical statistics and Bayesian statistics, because we're going away from our fixed population coefficient. But then if you have that, this random error interacts with the x variables and puts structure in the variance of the error term, which gives heteroscedasticity of a particular form. And this turns out to be a really easy test to do, because for all practical purposes, you regress the squared residuals on the squares of the explanatory variables. And you see if the fit of these squares is meaningful. So if there is no heteroscedasticity, then these squares of the variables should have nothing whatsoever to do with your residual variance. And so you should reject the null. They should not be significant. But if they are, if there is a relationship between the squares of these explanatory variables and your squared residuals, then you have a problem. That's the same as our graph where we have the funnel. There shouldn't be a funnel. It should be flat, right? So there shouldn't be a regression between anything, actually, for that matter, and the squared residuals. Nothing should be showing a pattern in the squared residuals. So if it does, then you have a problem. And then finally, the White test is a generalization of this concept. And it's not just the squares, but it's a polynomial. It's the squares, the cross products. And as it turns out, that is a really powerful diagnostic for a number of different things. And if you apply the White standard errors, then those are robust to a number of different misspecifications, not just heteroscedasticity. So as I mentioned, in large data sets, as we have this day and age, the lack of normality may not be that big a problem. It all depends on the central limit theorems that you use. One problem in practice is that it's very difficult to tell heteroscedasticity from spatial autocorrelation, as we'll see later. And the third issue, which is related, is that another way of putting this is that a test is designed to detect a particular type of misspecification, but in practice often has power to detect other types of misspecification as well. And we'll see that when we talk about Moran's I. Moran's I spatial autocorrelation test, which I mentioned the other day, applied to regression residuals, is a very powerful misspecification test in that it rejects the null a lot, but it rejects the null not necessarily for what you think it should reject the null for, which is spatial autocorrelation. It also rejects the null for heteroscedasticity, if there is heteroscedasticity, if there is non-normality, and so on. And this is the case for a lot of specification tests because it is always the same thing, right? You reject the null. You don't accept the alternative, right? That's the way it's set up in classical statistics. So if we have some device that can pick up deviations from the null, we reject the null. But we don't necessarily know why we reject the null. Right? We wish we did. And in a number of cases, if you structure it well enough, then at least you have some sense in which direction the alternative goes. Is it heteroscedasticity? Is it autocorrelation? Is it nonlinearity? Is it endogeneity? Those kinds of things. But in practice, you always have to be careful because these, if you carry out one of these tests in isolation, it may pick up other forms of misspecification. Okay, so this should all have been very clear or a refresher for most of you. Now we move into the endogeneity business. So we get a little bit more technical, but you can read this. If you're not familiar with this, you can read up on this at your leisure. So basically, we need this uncorrelatedness between the explanatory variable and the error term. And this is just three different ways of saying the same thing, right? The top two pertain to finite sample moments, you know, expected value or covariance. The bottom one pertains to an asymptotic condition. And the plim is the probability limit. So what happens to this particular expression as you go to the limit of the sample size, right? And you notice, or maybe you don't, but you should, one very strange thing in here. This is no longer x prime e, but it's 1 over n times x prime e. And why is that? Because in the limit, everything is infinitely large, unless you somehow rescale it to bring it back to something that we can compare. So if you have 10 numbers and you sum them, that's going to be much smaller than if you have 10,000 numbers and you add them up, right? Just by the nature of it. But if you divide the sum of the 10 numbers by 10, and you divide the sum of the 10,000 numbers by 10,000, you get quantities that are comparable. And then you can look at the randomness of these comparable quantities as n, the number of observations, goes to infinity. Because if n is infinity, and x prime e is a constant, you're dividing something by infinity, that's going to be 0. Okay? So that's not useful either. Keep that in mind. We'll get back to that in a few minutes. So it's all about rescaling these things that are random to keep them from being, on the one hand, infinitely large, which isn't useful, and on the other hand, 0, which is fixed and also not useful. So we need to keep them somehow random so that there is enough variability in them that we can model that mathematically. And that's why it's 1 over n comes in there, and later square root of n comes in there as well. So the simultaneous equation bias is just mathematically showing you what goes on. If we plug this in just like we did before, then no longer the second part drops out as 0. So the expected value of the ordinary squares estimate is no longer the population value. And the same thing holds in the limit. When we, instead of using the expected value, we use the probability limit, it's the same thing. Again, in the probability limit, the probability limit of the OLS estimate is not the population value. Okay? So we're in trouble no matter whether we're in the finite domain or in the infinite domain, right? It's this correlation that we can't have. So then we have instruments. So the general model, we don't write x anymore, we write z and theta, and some of the z's are correlated with the error term. And as I mentioned, you can't have that. It's signal and noise. They should be separate. So there's variability in both. How do we deal with that? Well, we cheat, right? We say, we don't want these variables. We're going to get some other ones. We call them instruments. And we'll get them so that they don't have the problem that we started with. So let's say in our crime equation, unemployment is correlated with the error term. We're going to get something else that is not correlated with the error term. What? The rainfall 2 months ago. Why not? It's uncorrelated with the error term, right? So that's okay, but that's not going to help us very much in terms of precision. What we want is not just something that is uncorrelated with the error term, but something that is somewhat related to the variable that we're trying to get rid of, right? So it has to be correlated with the original variable, but not too much. Because if it's too correlated with the original variable, then it has the same problem, right? Think of it, you know. You have a variable, unemployment rate, you know, and it's supposed to be, it is correlated with the error term. You're going to replace it by something else, unemployment claims, that maybe is uncorrelated. Well, but is it, right? It's highly correlated with the original variable, but if it's too correlated with the original variable, it has its problems too. And that is the quandary of instrumental variables. And nobody has a good solution for it. You have formal solutions, you have tests, but at the end of the day, you have to make it up, right? And it's whoever's story holds water at the end of the day. And I've read so many papers where people go through all kinds of contortions to come up with instruments that they somehow can defend as reasonably, you know, correlated with the original variable, but not too much, and uncorrelated with the error term. And that's, if you don't, this originally was developed, well, no, it wasn't, but the most intuitive explanation of these instruments is in systems of equations. And nobody does systems of equations anymore. That was a big deal in the 60s and the 70s, where you had a system with endogenous variables and exogenous variables, and then it was very clear that the exogenous variables that were in other equations, but not in your equation, could be used as instruments for the endogenous variables. So that was all very clean and very rigorous in a sense. Once you get away from the systems notion, then it gets a little shaky. You know. The bottom line is, you know, we have these instruments, and then we have a number of conditions for these instruments. First of all, we get a matrix of exact same dimension as the original matrix. Now, some of these variables are exogenous. They don't need instruments. So they're instruments for themselves, in some sense. So, but others are endogenous. We replace them by 1 for 1. So I want to be very clear in your head the difference between instrumental variables and two-stage least squares. A lot of people think it's the same thing, and it sort of is, but not quite. Instrumental variables is really 1 for 1. So one endogenous variable, one instrument. And so these two matrices are of the same dimension, and we need a couple of conditions, and I'll probably move fairly quickly over the technical stuff, but one is that you can't have them be multicollinear, okay? Usually that's pretty obvious, but sometimes it's not. For example, in the spatial setup, we'll have a spatial lag model that we'll talk about next week, and its problem is endogeneity. So then we need to have instruments, and some of these instruments, you know, as you can show formally, are spatial lags of the explanatory variables. But what is the spatial lag of a constant term? It's also constant. So you can't use that as an instrument because that would be multicollinear, right? So you typically don't have to really think about it, but sometimes you do. The other obvious condition is that the instruments have to be correlated with the original variables, and formally that means that the product of these two matrices, Q prime Z, has to be a finite rank matrix. So since they're both the same dimension, Q prime Z is a K by K matrix, and it has to be full rank. In other words, its inverse must exist, right? If it's not full rank, you can't do an inverse. That's what I meant when I say you need to be somewhat familiar with matrix algebra. So these are things that matter. And then finally, the thing that really matters is that they're uncorrelated with the error term. So with these pieces in hand, we can construct the instrumental variable, the IV instrumental variables estimator. And it's basically, as I said, cheating. So we're replacing Z, so OLS would be Z prime Z inverse Z prime Y. We plug the Q instead of the Z in two spots. So we have Q prime Z inverse. We can do the inverse because we said so. We assumed that it was a full rank matrix, so the inverse has to exist, and then Q prime Y. And then we can go through the different motions and show that this is in fact consistent. And the key trick here is that, you see the full matrices there, Q prime Z inverse, Q prime E. But if we go to the limit, as I just mentioned, we have a problem there with scale, right? So we have to rescale them, and luckily that's very easy to do because one is inverted and the other one is not. So if we divide both by n, we actually don't change anything. But what we do change is that we now have magnitudes that we've set up in our framework, because this probability limit of Q prime Z is here. This is a full rank matrix. And the probability limit of Q prime E is here. This is 0. So if we plug this in and we go to the limit, then we can show this first part is a constant that is non-zero. This is a random thing that in the probability limit is 0, so everything falls away and we have consistency. Now comes the tricky part. So consistency means that in the limit, your estimator is exactly on target. Okay. So what is the distribution of that estimator in the limit? It's exactly on target. The target is a constant. Constant doesn't have a distribution, so we're stuck. If you say the asymptotic distribution of the estimator, there is no asymptotic distribution because it's consistent, it's on target. So that's not useful, and this is this kind of mind game that you play to say something about this in a meaningful situation. Because remember, in practice, we are not in the limit. If we are in the limit, as I mentioned earlier, we're good to go. Our estimate for our population is the population estimate. Done, right? It's a constant. There's no variability there. But in between, as we move to the limit, so to speak, then it's not a constant. It's on its way to being a constant, right? So how on its way is it? What can we say about the variability of that estimate as we move to the limit? And in order to be able to deal with that, we actually play some tricks. So what we do is we take the difference between the estimator and then its limiting value, the value that it moves towards. So in the limit, this first part is 0, right? But because we're not in the limit yet, it's not going to be 0. And we scale it by the square root of n to make sure that it has enough variability, right? Because as we move to the limit, this is going to be smaller and smaller and smaller. So that's not really it's the same problem we had before where everything became larger and larger and larger, so we divided by n to keep it comparable, right? A lot of this stuff is about averages, and so averages you divide by n to keep them comparable. So here's the other way around. Here we scale it up by the square root of n to make sure that it's variable enough, that it's not too close to 0 to, for all practical purposes, become a constant. It's not a random variable anymore. So that's kind of the mindset. That's why you see all this stuff in textbooks and papers, and maybe the first time you see this, you say, why in the world do they do this? That's why you do it, okay? And so, again, because we have the inverse, we can easily carry this out on both sides of the equation. And then we know the first part, because we just saw it, this q prime z part is a constant. So in terms of randomness, we don't have to worry about it. So all the randomness comes from the second part. So what's the distribution of that second part? And so in asymptotics, there's two things. One is consistency. It's proving that your estimator gets you to the population value in the limit. The other one is to know something about this distribution, and for that you need central limit theorems. And central limit theorems tells you typically about asymptotic normality. But asymptotic normality in a very specific sense of the normality of the square root of n times the difference between the estimator and its population value. It is not the asymptotic normality as such of the estimator, because in the limit, that estimator is a constant. So it's always about what happens to the variability as you move to the limit. And so you need all these instruments. And that's what I meant earlier, where this day and age, you don't really need to assume normality as much as you used to, because you work with large data sets where you can use these central limit theorems to get normality even though you don't assume it, right? And so the tricky part will be for the spatial models to develop central limit theorems that take the spatial dependence into account, because your textbook central limit theorems, if you have had any kind of mathematical statistics, most of them assume IID, identical and independent distributed random variables, or they may allow some heterogeneity, INID, non-identical but independent, but very few allow non-independence because it's much more complicated. So then, just to kind of quickly run through this, the central limit theorem shows the normality of this second part, but then you have to kind of figure out what is this variance. We call that the asymptotic variance. That's the one we're going to use for the asymptotic t-tests, where basically at the end of the day, we act as if this is all finite samples, but we use the properties that we get from these asymptotics. So then the tricky part is to show that this M variance is actually consists of two parts. One has to do with Q, which is our instruments, and the other part has to do with the intrinsic variance covariance matrix of the errors, which we don't know, which is sigma. So if you assume that the errors are homoscedastic, then that is sigma squared I, then we have Q prime Q. It's very simple. But if we don't assume that, then it's not that simple, right? And so then you can look at this again. This just kind of writes it out. The notation gets very complicated, but it's basically, at the end of the day, this is the expression you have to worry about, right? So if sigma is spherical, then that simplifies. So then it becomes Q prime Z inverse, Q prime Q, Z prime Q inverse. This is the instrumental variables variance, not two-stage least squares. Okay, it looks a lot like it, but it's not the same thing. This is 1 for 1. Right? Okay, so then two-stage least squares. So far, we've said we have the exact same column dimension for Q and Z. Right? So what happens if you have more instruments than variables? Which ones are you going to pick? Right? So you could say, okay, I have, say, 5 instruments and 2 endogenous variables. So to do instrumental variables, I need 1 for 1. So out of these 5 instruments, I can take any 2. Which 2 should I take? Okay. And this is a classic decision problem, and it really has to do with solution of equations. You know, if you have more equations than unknowns, then you can pick them, you know, or it's the other way around. I can't remember, but whichever, you know. So what are you going to do? You're going to pick, in some sense, the best linear combination of the instruments. Right? So we still have the instruments, but we are going to take the combination of the instruments that is as close as possible to our original variables z. And formally, that is achieved through a projection matrix. And so if you look at this carefully, so you have q prime q inverse q prime z. That's, you can think of that as a regression coefficient, right? And that regression coefficient is multiplied by q. So that's a predicted value. So this is a predicted value that you get when you regress all of the z's, each of them in turn, on all of the q's. Okay. Now, some z's are not endogenous. So what do you get as the predicted value? So you have, let's say, you know, divorce rate is exogenous. And so then you have a bunch of instruments, but divorce rate is its own instrument, right? So if you regress divorce rate on divorce rate, what do you get? You get a perfect fit. So that predicted value is actually nothing but the original variable, right? So for the exogenous variables, this doesn't matter. It doesn't mess it up. It just keeps what you had to begin with. For the endogenous ones, it replaces each endogenous variable by the predicted value of its regression on all the instruments. And those instruments include the other exogenous variables as well as whatever instruments you came up with, right? And now we're back in business because now we have 1 for 1. So now we apply the same logic as we had before, our instrumental variables estimator logic, but we replace the endogenous variables by their instruments, and their instruments are actually predicted values, these ZPs here that we got from this additional step. And that's why it's called two-stage least squares. Okay, in one stage, we do this regression with the predicted values. Then in the second stage, we put the ZPs in there. And so then this is a very simple expression. You know, just like before, instead of Q, now we have ZP. Same thing. If you do a little bit of algebra, you can show that ZP prime Z is the same as ZP prime ZP. So then it actually is a ordinary least squares regression. Okay, so in the old days, before powerful software, that's how you would actually do it. You would run a regression, get these predicted values, using OLS, get these predicted values, stick them in a second OLS, two-stage least squares, and then you get the coefficients, and we're in business. So this is all good. However, the standard errors that the second OLS gives you are not the right ones. And so that's something to keep in mind. So the standard errors, the real standard errors, are the difference between observed, which is y, and predicted, which is z, times the thetas that you estimate. Whereas your second stage least squares gives you not z, but zp. because it's the second stage where you use the predicted values. So this is actually wrong. But then if you want to have fun, you can write out this whole expression. That's what it is. That's why these things get very complicated very quickly in terms of notation. But the easy way to think of it is in terms of this ZP notation. And just remember, these predicted values come from a projection, if you wish, which is a regression fit, the least squares fit, which is, the best solution to a system of equations where you have, whatever it is, more equations than unknowns. That's what it is. Then we're back in the same business. I'm not going to repeat this, so you can, as I said, read this at your leisure. The important one, again, is the sigma in here, okay? In the classic case, there is no sigma, and then this all simplifies out because you have q prime q and q prime q inverse, so they get taken out. But in the general case, this is this long thing. And just to, in a few minutes, I can show you. So we have this, it's one of the sample data sets. It's crime in counties in the US. So unemployment rate, I'm going to say, is possibly endogenous. And I have some instruments. I just made them up, but I have the data, right? So what are we going to do? We start with just a straight ordinarily squares. If this unemployment rate is endogenous, then these estimates will be biased, okay? So these are the first set of estimates. That's the standard output of GeoDa. Gives a bunch of measures of fit, and there's the coefficients and the standard errors and the t-statistics, all pretty standard. Okay. So now we're going to do stage 1 and then stage 2. So stage 1, we only need one. I mean, you can do all of them, but it doesn't matter. So the exogenous ones just get replaced by themselves. So we regress the unemployment rate on all the instruments, and then we get a predicted value. Then we plug that predicted value into the regression. So we, this is the regression. You see the dependent variable is unemployment rate, and then these are all the coefficients. In GeoDa, you can add the predicted value to the data table, and then you run the second regression, and you see on below, you have the predicted value of unemployment rate. Those estimates are the two-stage least squares estimates. The standard errors are not. Okay? And just to show you that, this is how you do it in GeoDa space. You just put the variable, we'll do this next week, you put the variables in the right boxes and then click the right model with the right type of standard errors. So this is the true two-stage least squares result. So here there's no predicted value of unemployment rate, it's just in there. And then it says, the instruments are, these variables that I used down there. Just to compare the estimates, so the first ones are biased, and you can see this, quote unquote see this in practice by noticing how the values are very different from the other ones. The second and third column are exactly the same. So the second column is to, explicitly do the two steps, OLS twice. The third one does the whole brute force thing in two-stage least squares. Exactly same estimates. However, the standard errors are not, because the first ones are way off anyway. The second column uses the wrong explanatory variables to get a true measure of residual. It uses the predicted values, whereas it should use the original z values. The third one uses the original z values. So the difference is not that major, but there is a difference. Okay, this is just an example. So this is about all I wanted you to know. So now we're all on the same page, so to speak. And then next week, we're going to start with spatial process models and spatial regression specification.